does your data support your hypothesis? And if you, which the answer is what, yes or no, but I can't leave you with yes or no. You have to explain what is the evidence for yes or no. So you're gonna go back to your data. What does your data show? You see that pattern in your data? No, you don't, do you? Now, do you really know whether or not that pattern is there by looking at the data you have? Well, we know there's some fundamental things like the more data you have, the more likely you are to see the pattern. And so the more leaves that you may measure may give this to you, may give you a better idea of the pattern. And that's what we look for in science. We're always looking for a pattern in nature. There's always going to be anomalies. There are always going to be exceptions, but in general, and in fact, what I try to tell my science teachers is teach the rule. Don't teach the exception. That's confusing to kids and adults. So if you're talking about mammal characteristics, you're not using the duckbill platypus. You're using cats and dogs and things that they know, so you're always starting instruction with the known and moving them to the unknown, where the duckbill platypus is going to be the unknown. So they're just fundamentals in instruction that apply no matter what the topic is. Excuse me. So, is there a relationship between galls and leaves, such as leaf size and gall numbers? Well, this was actually an investigation I told you earlier that our ecology classes did. And the reason this came about was because we were trying to teach our candidates, pre-service science teacher candidates, about types of investigations. And it was still kind of theoretical to them. And so one day I happened to say, well, you do this in your science courses. And one of my students said, well, yes, we do this kind of study in ecology and this other kind of study in ecology. So I said, okay, so I'm going to go from my students' known, which is the gall study, when I'm trying to explain to them what a correlational study is. But I have to start with descriptive because we call that we call it observational also, so you'll have a different kind of language for it. So in the ecology course, where's Luciano's? He's right there. So in the ecology course, here is actually what we say. So you're talking about Ross looking at statistics and all. Okay. So here's actually what we say. We are testing a hypothesis, and we state what the null is. So the null is larger leaves on average have the same number of galls as smaller leaves. Essentially, there's no difference. No matter if it's small or large, there's no correlation between the two. The alternative, number one, is larger leaves have more galls, or two, smaller leaves have more galls. So you go back and you're looking at your data and say, what do your data show? Remember, data is plural. What do your numbers show? And if you looked at your data, did it show any kind of a pattern? No, it could be too small sample size or other components, that might.
I'll tell you, ours did, but now that I look at the ones that we pulled, we pulled them in our favor. I realized that.
You're sampling.
I didn't realize it.
We had 3 labs.
We haven't gotten there yet. But they wouldn't have worked in our favor. So it's interesting. I'm like, oh, that one has, more.
Ah, okay. So we have to be careful about bias in our research, just like we do, because when we're measuring, the effectiveness of our program, we have to count everybody. Even if we've been in their classrooms and they're really not doing best practices like we have thought we've taught, we certainly recommend, we still have to include that in our data. And in fact, you remember what I told you, what we had found? It was not until the second fall, 170 hours later, that we really started seeing changes in instruction in the classrooms. And that's why we have, for the last 3 rounds, that we have required a 2-year commitment. Because if they don't make a 2-year commitment, you're not going to see a lot of changes. And we're putting a lot of resources, about $6,000 a teacher, in to make that kind of change. All right, so Ruby and Alexis did some stats for us, and so they did something similar to what you see there. And so Ross, here is what they did with it. They ran a linear regression equation on this to see if there is truly a relationship between the leaf size and the gall size. Because as Lori was trying to say, your data may look like some kind of pattern, but you have to measure it statistically. If you remember, well, it's in your notebook, that when we did the research on class size and increased accident rate, it was statistically significant that P 0.001. It was highly correlated. Overcrowding in classroom is highly correlated with increased accidents. So this is what matters. So we had a question when we were doing this professional development with our teachers a couple of Saturdays ago. At what level of math is this, number one? And number two, if kids are doing science fair projects and they're doing correlational studies, they're gonna have to run these. Now, they don't have to know this math. We actually have software. You just put your raw data in there and it will run it, for you to tell whether or not if there's any significant correlation between it. But this is what our students have to do in the ecology class is run a linear regression equation. So the conclusion was the slope of the line was 0. So when do you have slope? When do you teach slope in math? What grade level?
Algebra 1. It's big time algebra 1.
But it is not before, no, it's in 8th grade. It is in 8th grade, yes, because I know the conversation about changing the YAG came up with the slope. And in fact, just a slight reference, that when Candace, who is a fabulous science teacher, wanted to change the YAG, that was, the YAG, the year at a glance, the scope and sequence that Region 13 has. That she said it made sense to move motion later in the year after the students had learned slope in math. And that's why we said we need for you to be able to do that horizontal alignment and to see if it makes any difference. With the new math teaks in K5, that's going to be very significant. You lost something, huh?
I sneezed my earring off.
That's a pretty powerful exercise there, girl.
I got some skills. Got it. Y'all didn't know.
Everybody's gifted in something.
Anyway, so the bottom line is there's no correlation between leaf size and the number of galls that are on there. So in our case, at the university level and science fair, this is what they would need to do in science fair. Because I know in Lockhart, you guys had some big conversations about science fair and what would be appropriate to be doing at different grade levels. You had a big one at your. And the issue is that your science teachers need to understand types of scientific investigations and the associated statistics that go with it before you can actually guide students in doing science fair. A caveat, I would never require science fair for students. Okay, so there always has to be some kind of sense making, probably in any discipline. I know in science and math we have to. And I'll give you a teacher perspective. I taught 16 years of high school. I went to get my PhD, found out that middle school was a critical issue. If you look at the NAEP data, we lose kids between the 4th and the 6th grade. They start thinking that if they work hard, they can learn science. There's a question that asks that. I do well in science because I work hard. That's what those 4th graders say. When they get to the 8th grade, they say, because I'm lucky. They've lost the idea of efficacy. So I moved from high school to middle school because I knew that was the critical issue. So I started going to middle school and elementary professional development sessions like at CAS, the Science Teachers Conference, etc. So elementary teachers are so creative. I'm kind of left brain, 1, 2, 3 kind of person, secondary kind of person. And I go to these elementary workshops and they were fabulous. They were so creative. And we get to the end of the workshop and it would be over and I'd say, well, what was I supposed to learn from this? I know a lot of science. I should have been able to figure it out, but I could not figure out what they were trying to do with this activity, because we never ended up with this sense making. So in instruction in classrooms, we have to have that sense making, that debriefing, that's going to occur. So, we might think about things, what were the components of this design? So if you look at your, hold on, got a chart. Okay, pink sheet looks like this. These are the types of scientific investigations. Pull those out. Pull it out.
What's it called again?
Types of scientific investigations. Be toward the back. No, it's the next section. And it should be toward the back. Ah, Suzanne's found it.
There's a white page, purple page, and then that blue page. Is it in the best practices section?
Yes, it's all in the STEM best practice.
Okay.
Oh,
I see that.
why not?
Okay, once everybody found it, you need to look on your board. Yeah, it's past that black page. I think the shirts are back in there. The pink pages are products that we have developed. So that's kind of, so you'll know the lilac, remember, is research, and the pink are the products that we have developed. Aha, there it is. Okay, good, okay, Miss got it, okay, everybody has it now. All right, so what this is, I'm an Aggie, I like things that are simple and I can understand easily. So I created this, and I created it along with an article that I wrote that I'm not gonna ask you to pull out, but it should be together there, that I wrote that gives an example of, actually, I worked with a biologist from Baylor University, of how a student could move in biology from descriptive to to correlational to experimental. So you just went through a correlational investigation, and if you look at the center section, you'll see a check mark. So what were the components of the correlational design that you just used? Did you have a research question?
Yes.
Yes. Did you have a hypothesis?
Yes.
Did you have methods?
Yes.
Did you have variables identified? What were you measuring? So you were measuring area, you were measuring number of galls, so you had your variables identified. That's all you measured, the variables were kept constant. Did you collect data? Yes. Did you do any analysis? Kind of. No. I mean, you looked at it and tried to do some. Did you form a conclusion? Or not? You could have said, no, I can't really tell from this. That's still a conclusion. I can't tell from the data. I cannot answer the research question. That happens in real science all the time. We probably answer research questions 10% of the time. Most of the time we cannot answer them. So you have to not give up in science. You gotta just, have that grit to keep plugging along. Was there a control? Easy question, was there a control? No, there was not a control. So, you will notice in your chart here that there is a blank right there under descriptive investigation for a control and a correlation investigation. There's a blank for a control. You do not have a control in either of those types of investigation. There's no control here. There is a control over here. This is one of the research agendas that's going on. They're looking at growth of plants, and they don't label, well, they do, because I asked them to. I work with really great scientists. So I said, would you make your poster where it labels a control? Their control is called the wild type, because when I looked at it, I said, well, what's your control? And he said, it's a wild type. I said, okay, would you make me the poster where it labels a control? And so sure enough, where is it? I just saw it. He's got it labeled somewhere in here. Anyway, so there is a control. So this is experimental design. So what can I tell with a descriptive investigation? I can describe characteristics of the phenomena. In this case, galls on oak leaves. What can I tell with a correlational investigation? Whether or not there is a relationship between two factors. Is there a relationship? Many of you are operating on correlational data for your health. Does anybody in here have diabetes? Okay, so what do? What do you have to do because you're diabetic? You do and do not certain things. Name one.
Things I do.
Yeah.
I do check my blood. I do watch what I eat.
And why should you check your blood? Because the research says
That I need to
that
monitor
if
my
it
blood
goes
sugar.
up, then you need to do something, right? That is correlational research. We did not have controls where we said to diabetics, don't check your blood. So we don't, that's not ethical. So a lot of the health things that we do are based on correlational research because they're very practical for us. So correlations tell us a lot of things. And in fact, listen to this is important, Sally, you're gonna be surprised about this. That most of the research that is done in physics, in chemistry, is descriptive, correlational. It is not experimental with a control. You can't say, okay, stars, you stay still, and this one we're gonna move around. So you are not gonna have very many investigations that would be called an experiment. So you're gonna throw that word out of your vocabulary. No more experiments. That's a layman's term. It's also a term that we use up here, but we know what we're talking about. We use it kind of sloppily up here because we can. I hear it all the time in research seminars. You probably will too, but now you're gonna start being alert for it. So what we are doing for the most part up here are descriptive. If it's a new topic we don't know much about, or if we're trying to determine if there's relationships between things like the number of galls and the size of the leaf. That was actually one of the early research that was done by Dr. Ott with that. And then what kind of research design? Correlational. What do they call them in the TEKS? So they don't call it correlational. Called comparative. Same thing. That needs to be changed. We have a lot of problems with our science TEKS. So don't just stick with the TEKS. If there's holes, plug them. Okay, we already answered that. So what I was trying to get to the point today is for you to understand what you might be looking for in classrooms. You don't have to know all of the content, Patricia. You have cheat sheets, and you have language. As I said, we use experiments kind of sloppily, but if it means that there's a control, that's not true. And in fact, in science fair, Lori, that plays a lot in science fair. And I'll tell you a story, an old story, probably 30 years now ago. I had a 9th grade student who discovered a new species in the world. 9th grade, 14 years old, discovered a new species in the world. He was working with a scientist out of San Antonio. They were on Enchanted Rock, and they have what they call ephemeral pools that only fill up with water when it rains. And so they discovered this new brachiopod, kind of like a shrimp thing. And so he took it to science fair, to Alamo Regional Science Fair. He got 10 points counted off because he had no control. Well, you know me, I just said, are y'all crazy? You don't have a control with a descriptive study. This is a new species in the world and you're saying it's not good enough to go to state? So I got the Texas Academy of Science to start writing position papers about this, and that's how we started getting it better into the TEKS and hope to continue to improve it. So your little children at the K-5 can do these kind of correlational studies. But you know the questions that I had you design a while ago and try to raise them to a higher level? How many of you asked why? How many of you had, you don't know why unless you have experimental design with a control. So I tell my science pre-service teachers, stop answering questions about why, because most of the time we don't know why. We know it occurs, restrictive. We know it occurs in certain instances, correlational. Do we know why? Not until we have a control can we do that. Or a situation where you can have control, like in microbiology, you have controls. Remember the little discs that you have with the antibiotic? A lot of you have seen those. Well, at least some certain science have. But you can have controls in certain of the disciplines. Biology is easier. It's harder to do out in nature, but I can give you examples where we've done that, for example, with antler size and body size on deer for hunting purposes. We know that there are two things that control that. One is nutrition, which shouldn't surprise you, those genetics. And so they say if you've got a rut buck, shoot them. They're never going to get big enough for you to be a good hunter choice. Okay, so I want to alert you to a couple of things, and then we're going to take a break. We have talked about this one right here, this 3 lesson planning principles. So I'd like for you to pull that out, if you don't mind. It's lilac because it's based on research. We thought we were being really clever with the kind of dividers that we had, and it's apparent we'll be getting some more. We're sorry, y'all are guinea pigs. Oh, before the black page.
Yeah.
Before the black page. Good thing we have that black page in there. That's a good marker, isn't it? Okay, does anybody have it here? Before the black page. That's the black page. All right, so first of all, I want you to note on the back of it the date. This is not the latest version. So when y'all get handouts from us, always see what the date is and see if it's the latest version. I will give you a copy of the latest version. So what we have found in terms of what the research tells us is these things are pretty fundamental. Concrete experiences before pictorial or representational before abstract. In general, we say words and numbers are abstract, but there's more to it than that, as you might guess. Known to the unknown, which we've talked about, and then the idea of limiting instruction. One concept per lesson. You overload kids with too many concepts, they're not going to learn them all. So, in general, and the way we try to convey that is with this kind of shading that we've done and the divisions here. So you'll notice there's squiggly lines here. There's not straight lines. You see that? Mm-hmm. Because it's not a rule, it's a guideline, and sometimes things kind of fade into one part or the other. And then you'll also notice a shading across, because again, sometimes there are practices that are clearly here, and sometimes they kind of morph over kind of more toward this area, if you would. So that's the idea, is to say, these are not rules, these are just general guidelines, these are things for you to think about. So if we look at concrete experiences, the idea is the mind cannot forget what the hand has learned. I went through a very interesting experience one time where we had, we were get in teams of 2. I was with an elementary principal who knew nothing about science. So when I went over to get one of the objects that we were supposed to get, I chose something that I knew he would not recognize. And so I had to go over, keep it covered. And so he had to close his eyes, and I had to hand it to him, and he had to draw it. Okay. And then after he drew it, then I would hand it to him, and he would draw it from looking at it. And then he would trace it. Well, what I picked was the 2 earthworms that were copulating with their flagella showing, okay? And I knew he wouldn't know that. Only Sally and I would know that. Anyway, and so guess which drawing was the most realistic? I'm giving it away. What he felt, not what he saw. The best drawing was the one that he felt, and that was true with the whole room. So the idea that the hands cannot forget what the mind cannot forget what the hands have learned is just critical in terms of giving kids these kind of concrete experiences. So what you see here are examples, both in science and math, and we actually have expanded these a lot to give better guidance. So tangible objects, experiences where students touch, feel, smell, etc., using models, kinesthetic, field trips, specimens, math manipulative. So all of these are what we would call kind of concrete experiences. So notice the difference between the first example in concrete and pictorial. In the first example, the students graph data or they draw their specimens. In the second example, they look at them. So they're looking at someone else's drawing or whatever. The first one, they are drawing it, they are feeling it, they are graphing their own data, which is more concrete than looking at somebody else's data that's graphed, for example. So what we have down here are some examples of concrete, and then how it would look at the pictorial representational, and then finally what is abstract. So algorithmic behaviors, that's not the right word I'm using. In other words, just starting to work math problem is starting abstractly.
Reasoning.
Pardon?
Reasoning.
Okay.
Algorithmic reasoning.
Yeah. So the idea is with these math manipulatives is that they are learning, they're understanding it conceptually because they're starting at a concrete level. And that is not what we're seeing in classrooms, and we are not seeing students understanding. Sometimes it's really strange to get a glimpse into children's minds. I love teaching. I love being out in your classrooms because I learn so much. I was out in a 7th grade student teaching classroom, and the kids were having this one where you go from cells to tissue to organs, you know, that stair step that you learn. So there's this one little kid, and I was walking behind him, so there's one little kid. He was sitting there, and he was kind of bedraggled, and you know, he looked like one of these at-risk kids. And so I started asking him questions, which I learned to do actually many years ago from a good friend of mine. And I mean, it seemed so obvious. They had these pictures, you know, that you typically see. I'm thinking, why didn't he get it? It just seemed pretty obvious to me. And so I started asking him questions, and so I finally figured this out. So you've got these 4 areas here. So these are cells here, and this is tissue, and this is organs. No, I can't spell it right. And then these are systems. All right. So he's here, and so he's seeing these cells, little things, you know, and these cells, little things, etc. And he couldn't get beyond this. So he's here. And so I said, well, what if we do this? We take these cells and we do this and we get this tissue. Now that doesn't take a genius, but what is it in instruction that did not get that kid from here to here that seems so obvious and so simple? Something is violated. When kids don't learn, fundamentals have been violated. So with my students, I'm saying, okay, go back to the basics. It's like, who's that football coach from, California? Can't remember his name, you know him if I said it. But when kids were making a mistake, he would start off practice with, this is a football. He told kids how to put their socks on, how to do all of these kind of what things that you think are simple, but that's what it took for a winning team, is to attend to those basics, attend to those things. Okay, trying to make sure I've alerted you to all of these. So here's the article that explains it a little bit more there. And then I want to go back to this handout, if you would. And I want to explain this to you. Everybody go back to your handout. Yes. All right. What? Oh, right behind the PowerPoint, right, yeah. All right, so you know what the top part says. You understand that part. There is a blue column, and that is drawing from the framework. All of this language is drawn from the framework, so there's no inconsistency here. So this is describing the scientific and engineering practices that relate to these assessments up here at the top. So the blue are the scientific and engineering practices. The yellow is actually what we would call, or the orange, is what we call the content. So if you want to know what this assessment, or these assessments are assessing in content, you go to that middle section. It tells you exactly what the assessments are assessing. And someone asked that question earlier, and I said we would come back to it. The last one is cross-cutting concepts. So we have big ideas like cause and effect and scale, proportion, and quantity. Those are big ideas in science as well as other areas. So they're showing what the scientific practices that relate to this, these assessments at the top, what discipline, the science that this is assessing, and then what kind of cross-cutting ideas that this relates to. At the bottom, and I think I can say it now without being strung up in Texas, it links to the Common Core. So, which is a good thing. Because what it does is, if you look at the bottom, it has R for reading. It says ELA and literacy, draw on information from multiple print or digital sources, yada yada. And then it has the math standards that are in there in Common Core. And it says if students are learning this science, this is the math they'll use to learn it with. And what else is in there? I don't know, but anyway, you see what it does. It does that crosswalk, if you would, that makes all of those links, so this makes some kind of sense. This is a very powerful standard because it synthesizes so much for us, but it's dense. I can't tell you how many months it has taken me to figure this out and how to use it well. So we will be doing this a little bit with your teachers. What we are recommending is that this lesson plan format that we have our lessons are in it. You have a copy of this second grade one in there. And so what you will notice, it's based on the TEKS, always. And it has the prerequisite science and math in there. And then you will see all of these standards. So it has the TEKS, it has the two old standards, the 1993 and 98, I believe. They're still good though. There's nothing wrong with them, so that's why we're including them. Then it has the two new standards, the framework and the NGSS. Because if you really want to understand what this TEK needs to teach or learn, the students need to learn with it, you need to look at all of these standards. It will help you, Patricia, to understand that content. Now, we know, as I said earlier, teachers don't have time to do this, but if they're studying their TEKS, they better start reading this stuff. They better start making some highlights and some notes in those books, one of the many books that we've given to them.
Do you have the other grade levels?
In the lesson plan?
Like this is, yeah, no, just the way this format is that?
No, we have it, well, this is the second grade, we have fifth grade and we have some sixth through eighth ones that we're going to start out with Monday with your teacher. We're gonna start out with this second grade one here. Because remember we said the particle nature of matter is not well developed in the TEKS. That's why when they get up to high school, they're not understanding IPC and chemistry and physics. They've memorized up here, but they don't have this foundation down here. It's interesting on the misconceptions is that they don't understand that you've got a molecule here and a molecule here, and there's nothing in between it. There's not like syrup, it's not continuous. That matter is made up of particles. The particles could be atoms, the particles could be elements, the particles could be molecules, one other thing I forgot what it could be. But anyway, the idea of the particle nature of matter. So we have these samples, but what we hope to do is to teach the teachers how to access these resources so they can understand it better. There is a handout on, I'll go with this one. There's several handouts on what used to be and what should be in there, changing. You don't need to look at it now, I'm just telling you. That there is, in fact, one of the main things you see is less emphasis on vocabulary. All of this stuff about academic vocabulary is really undermining science and math instruction because it just ends up being memorizing vocabulary words. That's not understanding. Do they end up with it? You betcha. But they don't start with it. And that's not the whole focus. And you will notice when we talked about this earlier that in this format there is a place for important academic words and non-academic words like cycle is a general kind of term. So we've had them identify those as well because they may need to teach what a cycle is, for example, if maybe the ESLs or something. So the idea of what's old and what's new, what the new recommendations are, and then there is in another page in there that talks about the 5E. Now, from yesterday, I want to leave you with two things. First of all, not every lesson should be direct instruction, and not every lesson should be inquiry. You have to have, that's your professional decision that you see what is to be taught and decide what kind of instructional model that you need to use. And we showed yesterday that there are places in an inquiry, in a 5E, where you have to use a direct instructional model. A lot of times it's in the explore. If they're using a piece of equipment or if they're filling in a chart, etc. So it's, it can be mixed in there. It's not either or. And that's where those professional decisions have to come in. The idea of the kind of instruction that has to be taught is there's no charts, there's nothing like that we have. Because it's too big. We have to teach the fundamentals and then the teacher makes those professional recommendations or those choices. And one of the things Denise and I talked about, the importance of having teachers having these conversations about what should be done this way or that way, to deeply think about things. They may not come to the same conclusion about it, but they've thought about it. There are times Denise and I disagree, or Browning and I disagree, and sometimes, we do it in front of the teacher so they can see us how we have kind of, have this civil discourse while we disagree about things. And, but I can tell you that anytime somebody disagrees with me, I'm going to be thinking about it later on. I may tell them at that moment I don't agree, but I can promise you that I will be thinking about it right after I've left them and for a long time afterwards. So that kind of, discussions are important to decide what kind of instruction that we're going to have. I had another student teacher that I went into the classroom, and so I always try to get the feel of the classroom, what's going on and how I'm going to have to guide, because a lot of what kids learn here they think is theoretical. They don't realize it really is not. But anyway, so I have to sometimes make that bridge between theory and practice for them. So I went into this one classroom. The room was beautifully organized. I mean, she had a fabulous organization system going on. So we started talking about instruction. She said, well, I use the 5E. Well, when somebody tells me they use the 5E, I've got a red flag going. I've been using 5E for 25 years, so I know a lot about 5E. I've worked with the BSCS in Colorado Springs, which was where it was created. So I always have a red flag, and I said, well, tell me about it. She said, well, on Monday we do the Engage. I almost cried. I kept a straight face. And I said, really? And so how do you do that? I think, well, that could be a possibility. I'll be open. She said, well, we have them define the vocabulary words. I said, well, you know, that's not exactly how the 5E is designed. Where did you get your training? Region 13, alternative certification. So, you know, I'm in this dilemma because my student knows the correct information, but I got a total cooperating teacher who does not. So I've got this dilemma that I won't go into with you about how I've got to negotiate that with student teachers. That's why I said it's so important, you know, that we're all on the same page and we can have these conversations with the interns or the block students that are in, plus the student teachers that are coming into the classrooms that was over class. So a 5E can be a 6E or a 7E. It can last 15 minutes. It can last 3 days. So there's a lot of flexibility there. All right. I have saturated your brain, and it's time for a walk and talk. So if you want some water, there's some water out there in the cooler, and you can take a lap.
Turn right around the corner.
Okay, so what questions do you have? You're at same all. Yeah.
One point is not this, like it's a misconception. Like people think, well, this is my one point. To the general public.
No, we're yesterday we did math. She did a lot of math.
If I recall correctly, I'm not
It has a lot of formulas on there, I don't know.
yeah. Usually not much, they all have
I just,
I don't know.
five.
They still have this calculation. These are jokes.
Ross is the curriculum director, secondary curriculum director at Lockhart. Hi, how are you?
Good.
Nice to meet you.
I work with the coordinating board. Pleasure to meet you.
Yeah, she's the one who asked the hard questions.
I'm paying attention to the word.
So Ross is new to Lockhart,
Okay.
and we have a really great relationship.
So what is this? Oh, you're doing total number of students, okay.
Total number of tests.
Gotta have teachers
Uh-huh.
We've got 70
Right.
test
in
takers.
order
Third
to
grade.
make a change in the
Right.
We've got 70 test takers and we have 200.
Well, you do, but you're not the only ones.
Okay.
And, you know, my Lockhart's near, so it's
Okay.
about, what, 18 miles or something, it's
From
not
here?
far.
Okay.
And so our program needs to be improved. And I went to the district while Lord moved out.
Cause how do you get this
7 years
information?
now, so, his boss, Dr. Brown, was his principal, and he and Dion worked together in Seabog and our STEM candidates are scattered, so they're having to make geography lessons, science lessons, math lessons. And so I had proposed to the university that we develop STEM campuses. And I like Lockhart to be those, and so we would put our STEM, what we call our blocks. So the students, the high school students take one block, so they're out in the school one semester, and in the morning they have coursework, and in the afternoon they're out in the classroom. So they're gonna be meeting, the classroom will be at Diana School that they're gonna be using, so they're starting small with one elementary cohort at Lockhart at that school. And so the idea, is to create this exemplary experience for our students, but also to improve instruction. Because we're gonna be working with the teachers, but it's kind of an enriched environment now because we have mix.
Right, and when that industry is growth, so it has to be the growth.
So the idea is to improve instruction from a lot of different directions. And then, they tell us, you go in the classroom, you tell us what you see,
I recall,
and we
it's
can
been a while.
include it in our instruction.
Right.
Our questions. And we have a huge consideration.
Just playing with this.
I just
We
saw
make
this.
teachers videotape themselves. Debrief.
So email her today.
That's your side. It's like, Denise and I,
They have.
say, oh,
Can't blame her.